Okay. So thank you very much, Darshan, for a nice introduction. So it is my pleasure to be here to deliver a lecture on control of cracks development and reinforced measure in structural design and construction. So the program is a faculty development program, AICT Atal program, right? So let's do not waste the time. We can start the right away the lecture. So as you see in the front slide, right? So main topic is the cracks development. So here the how we can control the crack in the reinforced concrete, right? During the structural design, even in the construction also, right? So main thing in the structural design. So which kind of precaution we need to take care and how we can control. So what will be the depth of the crack? So what is the width of the crack with a different code of practice? For example, Indian standard, American standard, Canadian standard, British standard, Egypt standard, Australian standard. Right? So we'll be discussing about each and everything in the detail, right? And later on, we'll be discussing about that construction practices. In construction practice, what kind of precaution we can control the cracks, right? So here you can see some of the photographs is available. Yeah, here you can see some photograph. For example, this is a bridge girder, and these are the okay. So for example, we can use that epoxy also or some of the rich mortar also. We can fix the structure. So eventually we need to see like what will be the service life of the structure, right? So main thing is the service life of the structure, how we can predict. So that is related to the serviceability criteria. So here we can discuss, let's say, what is that cracks. Like concrete is the most widely man-made construction material in the infrastructure projects. So here you can see cracking is a common problem in a concrete structure in the real life service conditions. So here in this particular photograph, so you can see how the cracks is developing. So crack-free concrete structure are very rare to find in the real world practice. So here let's say you can say construction practices, the concrete structure. These are the these are the fresh concrete. These are the hardened concrete. So here some of the structure. So you can see some the crack here. So here you can see all the cracks is developing. So it's randomly organized the crack. So here also all the cracks you can see these are the existing structure and these are the hardened structure. So how we can say how this crack is affecting for the use the safety of that particular structure. So which will reduce the service life of that particular structure. So main thing is that there are the huge vast economical loss of the infrastructure here. So concrete can undergo early age cracking, so depend on the mixed composition. For example, another is the environmental exposure condition. The severe environmental exposure, normal exposure, like a aggressive environmental also. Sometimes the temperature effect also, like heat of the hydration and the curing condition. So main thing is the curing. So if you are not able to apply the proper curing in the reinforced concrete structure, the structure is not going to become a durable. Even if you are not making the proper water cement ratio, even you will find there some shrinkage crack. So different kind of the shrinkage crack, and if the concrete is going to get hardened, so you will see some of the plastic crack. So let's discuss about the what kind of the crack. So before the hardening and after the hardening. So concrete once it's getting setting, so that we can say after the hardening and before the hardening, once it was in the initial setting time. So we can say that is the before the hardening as well as the after. Before the hardening, we can say construction movement, plastic crack, frost damage. After the hardening, we can say volume instability, structural design, and the physical or the chemical. So we can say construction movement like formwork movement. If your formwork is not properly, then there is a chances of the crack. Sometimes the subgrade also. For example, let's say construction, like rigid pavement. In the rigid pavement, so there is a cracks on the subgrade also. Like if there is a movement on the ground, so there is a chances of the cracks in the subgrade. Like we can say plastic crack. So plastic like plastic shrinkage also, plastic settlement also, and autonomous settlement also. Let's discuss about the premature freezing, scaling, crazing. So these are the some of the types of the cracks. So like volume instability, drying shrinkage. So how we can say drying shrinkage. So once the concrete is getting drying, so if that proper curing is they are not applying, there is a problem also. Thermal changes, creep also. Creep, so that is related to the long-term duration, like sustained load also. Like and now let's say hardening. After the hardening, like during a structural design. So once you are calculating the load, intended lifespan also, like a design and subgrade also, fatigue load also, alkali silica reaction, alkali aggregate reaction. So here we can say alkali silica reaction as well as the alkali aggregate reaction, like steel corrosion, freeze thaw cycling. So these are the cracks is going to develop in the reinforced concrete structure. So that is the before the hardening as well as the after the hardening. So you can say here this was the fresh concrete. So before the hardening, so it's like initial stage. So this kind of the crack is going to develop. But if you say after the hardening, so these are like after the 28 days or like let's say few days, so there is this kind of randomly oriented crack is going to develop. Because of the crack, the concrete is going to make a problem in your reinforced concrete structure. So now, if you see the in the atmosphere, there is always carbon dioxide is there, oxygen is there, water is also available, right? The moisture. So the moisture will penetrate through this particular crack, and it will penetrate inside of the concrete structure, and it will affect to the reinforcement, and then corrosion will start, right? So we should have to reduce the crack even the before the hardening as well as the after the hardening. So how we can say the how the cracks is going to happen whenever the structural member subjected to bending, right? So it's generally series of the district or the flexural crack even at the working load also. So let's consider one of the example. Let's say RCC beam. So depth of the beam is a D and the breadth of the beam is a B. Let's say now we are applying a sustained loading. So this is the one of the tensile reinforcement here. Here you are applying the loading, right? Axial like the gravity load. So because of that particular working load also there is a chances of the crack. So here you can say these are the tension well as the compression zone. So the compression fiber it will get compressed here. The tensile fiber here it will develop the tensile forces, and because of that particular force. So here you can say some of the cracks is going to develop. So tensile stresses is greater than the tensile capacity of that particular concrete structure. Then tensile stresses, and then crack is going to develop. So these cracks are unobstructed and harmless unless the width become excessive. Some of the cracks is permissible to the code of the practice, right? But if it is going the beyond that permissible limit, so it will be the harmless crack. So here we can say some initial crack is going to develop because of the sustained loading. Okay, so yeah, here we can say secondary crack. So the cracks is going to develop in the concrete structure, something like here. So you can see how the crack is like a web shear crack. So because of this particular sustained loading, the flexural crack is going to develop, shear crack is going to develop. So in which case, apprehension and durability to the concrete in the extreme tension fiber of a beam section is expected to the crack for the first time when the stress reaches the value of the modulus of the elasticity. So here we can say once the tensile stress is a greater than the tensile capacity of this particular structure, then the crack is going to develop. So crack will be shear crack as well as the flexural crack. So cracks in the concrete structure are common occurrence, so which develop when the stresses in a component exceed the tensile stresses. So here you can say for this particular animated videos also, so because of the system loading, so cracks is going to develop as well as beam, slab and the column also. Let's consider this is one RCC frame structure. So where the cracks is going to, so here let's say you can expand that particular beam. So here you can say there is a flexural crack, web shear crack also. Right? So cracking of the concrete section cannot be prevented, but size and the location of the cracks can be controlled. So how can we control? Right? So this way, let's say using the proper reinforcement, placement of the controlled joint also, and the better curing practices. So this way control the crack. So once this particular crack is going to develop, whether it is a flexural crack or the shear crack, so we can control the cracks or the size and the location also by providing the proper reinforcement detailing also. Once we are providing the joints also, so it should be proper joint and the better curing practice like construction practices as well as the curing practices. So causes of the cracks. So why the cracks is going to develop? So load induced cracks, so which will be about 5 to 10%, which we can consider the structural crack. Deformation induced crack, so which will be considered the non-structural crack. So 80% or more crack. So let earlier what we have defined, that was a that before the hardening, right? So plastic shrinkage also, self desiccation shrinkage also, drying shrinkage also, so these all cracks because of the humidity change and the temperature changes. Once the temperature of the atmosphere is going to change, concrete is performing different way and the cracks is going to develop. For example, let's say once we are casting the concrete, let's say in the early 4 o'clock in the morning, right? So the concrete, so cracks will be different. If you are casting the concrete 8 o'clock in the morning, so crack pattern will be different. Same concrete, everything you are keeping the identical. Same concrete, if you are casting at the 2 o'clock at the afternoon, so crack pattern will be different. So how we can control this construction practices? So these cracks sometimes we can say alkali aggregate reaction, right? AAR. Sometimes freezing and the thawing, uneven expansion, bad soundness, and different issues also, right? So how we can control all this crack? So that the crack is the load induced crack as well as the deformation in the causes of the cracks in the poor construction practice also. So poor construction practice we can say, for example, if you are adding the more water in the concrete, so it will increase the workability. So what will be the effect in the practice? So which will reduce the concrete strength and increase the settlement. And what will happen? So increase the drying shrinkage as well as the plastic settlement crack is also going to develop. If you are increasing the cement content to offset a decrease in the strength of the adding water. So what will be effect? Which will affect the temperature differential between interior and the exterior section also, and which will increase the volume of the cement pad. Eventually, which will increase the drying shrinkage as well as the thermal. If you are not applying the proper curing practices like inadequate curing, so at the time lack of the concrete hydration, which will decrease the compressive strength of the concrete. So what the factor is causing to increase the shrinkage at a time when the concrete as well as the low strength. Another thing is the lack of the support form. So if you are not applying the proper formwork also, inadequate and the incorrect placement of the construction joint also, what will happen? So which will increase the settlement, insufficient support for the setting time concrete zone at open at the high stresses also, and eventually what is the factor is causing? So concrete cracks from its load before it has developed enough strength to support the itself of that particular concrete structure also. So that is the main reason of the poor construction practice also. If you are not applying the proper construction practice, proper curing condition also, then cracks is going to develop in the reinforced concrete. Let's consider one of the examples, square beam. So how the cracking process is going to develop under the action of that particular sustained loading. So let's say we can apply the loading of this particular structure. Let's say it's a simply supported beam here, right? Here we are applying the forces. So here we can say, let's do the load deformation diagram. So load in the y-axis, deformation in the x-axis. So here we can say, because of the force, this kind of the tension stiffening of the cracks is going to do. If you are applying the imposed deformation, once you are applying the imposed load, so the crack pattern will be different. If you are restraining that shrinkage, right, so at that time pattern will be different. So cracking process differ depending on the whether it is caused by the external load, imposed deformation, or the restrained shrinkage. For example, if you are applying the boundary condition, fixed condition, right, for this particular structure, so at that, so now you are restraining the support condition, so cracks pattern will be different. If you are applying the import loading, imposed deformation also, the crack pattern will be different. All reinforced concrete beam elements, so for example beam, column, it will get cracked, right? So generally starting at the load well below the service level and possibly even prior to the loading due to the restrained shrinkage also. The flexural cracking due to the load is not only inevitable but actually necessary for the reinforcement to be used effectively. So this kind of the cracks, you can say, why the vertical crack? So it is running parallel to the longitudinal reinforcement. So because of the corrosion of the longitudinal reinforcement, this vertical crack is going to develop. So diagonal crack. So here we can say which is the shear crack. So why that kind of the crack? Because of that the inadequate lateral reinforcement of this particular reinforced concrete structure. Another crack is the horizontal crack also. So this kind of, if you are not applying the proper curing condition, proper support condition, proper material quality also, this kind of the crack is going to develop. Sometimes the some crack is going to develop like a splitting kind of the crack also. So prior to the formation of the flexure crack, the steel stress is no more than the n times the stress is in the adjacent concrete structure. So what is that n? So n is that modular ratio. It is the ratio of the modulus of elasticity of the steel to the modulus of elasticity of the concrete. So that we can find out the that modular ratio. Let's consider one of the RCC building, right? So once you are applying the loading, so where the cracks is going to develop. So because of the loading, so the shear crack as well as the flexural crack is going to develop. So these kind of the cracks we can say inclined cracking. So like these are the inclined cracks. So that is the shear crack. So which will be with respect to the horizontal, it will be 45-degree angle. So that kind of the crack we can say flexure shear crack. These kind of the crack we can define as the flexural crack. So here we can say because of the gravity load also this kind of the crack is going to develop. If the crack is developing like that, here this kind of the pattern 45 degree to the, or we can say diagonal crack. So that kind of the crack is going to, it will be the shear. So sometimes like changing the force condition of the concrete structure leading to the local or even in the overall failure of the structure. Once you are testing the structure, like here we can say these are, so for this particular beam, if you are testing for the under the action of the gravity load, the crack pattern will be different. So which will weakening the stiffness of the concrete building with the dynamic changes of the environmental condition also. Eventually, which will reduce the seismic capacity of that particular structural member, and which will eventually it will affect the stability and the safety of that particular reinforced concrete structure. So this particular structure has been damaged due to the earthquake. So this photograph from the Bhuj earthquake, which was occurred in the January 26, 2001. So the cracks deteriorate the structural durability also. Like for example, we can define in the layer also, which is accelerating the transmission of the environmental aggressive media, air, moisture within that concrete structure also. Next, we can say number three. So here you can say stage number three. So now because the corrosion, the cracks is going to develop, and so now so once the H2O, air and the CO2 will penetrate inside of the concrete structure, which will touch to the reinforcement, and the reinforcement is going to start the corrosion. So we can say shortening the activation and the corrosion time of the reinforcement, which will reduce the service life of that particular structure. So let's discuss like before the designing of that reinforced concrete structure. Let's we take some of the assumption. Why we need to take an assumption? Because whatever the laboratory practice or the design practice we are doing, so it is not necessary there. So that particular structure is going to happen similar way, right? Because in the field condition, it is going to happen different way. So therefore, we need to consider the factor of safety also, and we need to take some of the assumption we are considering. For example, plane section remain plane, right? So plane of the strain in that particular section remain plane after the deformation also. There is a perfect bond between steel as well as the concrete. We are assuming that there is no slippage occurring for this particular structure. There is no any slippages, right? So that is our assumption. Another thing is that like a behavior compressed concrete. So the stress strain behavior is the linear. So here we can say stress strain behavior will be the linear behavior. So and the design of the concrete structure, we are ignoring the tensile strength of the concrete. So tensile strength of the concrete, which will be about 10% of the compressive strength of the maximum compressive strength, which should not occur 0.35%. Why we are considering the 0.35%? For example, let's say you can test the concrete cylinder under the action of that particular loading. Once you draw the stress strain diagram, so the maximum strain will be about 0.35 here, at regardless of the grade of the concrete, because the ultimate strain will be 20 ampere concrete, 50 ampere concrete or 80 ampere concrete, but ultimate strain will be about a 0.35. Here we are considering linear behavior of the steel under the tension as well as the compression also, like stress strain diagram of this particular uh, uh, that mild steel reinforcement. So it will get yielding like upper yielding point, lower yielding point, ultimate strength as well as the fracture here. So what we are discussing, like we are ignoring the tensile strength of the concrete, because here you can say this is the compressive strain. So compressive strength will be higher, but the tensile strength capacity will be very low. It will be about 5 to 10% of the compressive strength of the concrete. So therefore, we are neglecting the tensile strength in our structural design. But we must have to consider the tensile strength of the concrete, because it depends on your condition. So what is that limit state of the serviceability? So which is dealt with the functional use of the structure under the normal loading. So they concern the functioning of the structure and the comfort of the people. So that is related to the strain, vibration, cracking, and the major serviceability like excessive width, right? So that is which means crack control, excessive crack width, so related to crack control, excessive deformation, so how we can control the stress limitation, so stress limitation which is related to this material, steel as well as the concrete. And another is the undesirable vibration, then vibration, thermal, sound, insulation. So these are the some of the limit state of the serviceability criteria. So let's say this particular structure we are applying the this gravity load, and the structure has been supported with the simply supported. So once we can draw the load versus deformation diagram, so we can say the because of the load, so there was some initial crack is going to develop. Later on, the limit state of the serviceability criteria for this particular region. So yielding of the reinforced concrete member here. So the steel reinforcement is going to yielded. Later on it will go to the ultimate state, limit state. Eventually the structure is going to fail. So whatever we are designing our structure, so it should be satisfy the serviceability criteria of the limit state. So limit state serviceability criteria. So main thing the crack control, deflection, right? So crack control and the deflection of that particular structure. So that limit state of the serviceability criteria. So we need to keep in mind during our structural design. So in order to guarantee the serviceability of the structure, the resulting crack width should be limited to the acceptable values, right? So code of practice has given some of the acceptable values, so that crack width should be within a permissible limit. So the current design of the code of practice which regulate the minimum reinforcement for the crack width control by taking the cracking force of the section to relevant of that particular part also. And the distance between the crack is usually assumed to be given by the reinforcement also. So this particular structure we can say the bending and the flexure create high tensile forces which can cause it the concrete floor slab to the cracking. So whatever the forces we are applying, so because cracking the tensile due to the bending also, these kind of the crack is going to develop for this particular structure here like shear crack, so which will be the diagonal shear crack, and here some of the flexural crack is also going to develop. So because of the excessive bending, so the stress is going to develop. So that will the because of the high tensile forces, the bending stress is going to increase, and then flexural as well as the shear crack is going to. So how we can control the crack? So that crack should not be unsightly or the wide enough to lead the durability problem, right? So main thing is the durable structure, so which is depends on the structural parameter, for example, steel concrete bond and the minimum cover requirement. So what is the deflection control? Appropriate limiting value of the deflection. So here for this particular structure, you can say shear tension failure, shear compression failure also. So once you are designing the structure, like for example, whether it is under reinforced section, balance section, or the over reinforced section. So here you can say this particular crack is going to develop because of the loss of the bond due to this particular crack. So because of the crack, so there is a bond is going to lost between that crack, this steel reinforcement, this concrete structure inside of that particular structural element. But even in structural design, we have assumed that there is a proper bond between steel as well as the concrete, right? So now our assumption is going to fail. So therefore, many times the disaster is going to happen. So therefore, we must have to take care during the structural design also. Like here of the this particular, let's say, bridge structure also, deflection at the limit state of the serviceability. So this particular deformation of this particular slab which should be within a permissible limit. Let's consider the cracked section as well as the uncracked section. At small load when tensile stress are less than the modulus of elasticity, so which we can say bending tensile stress at which the concrete begin to crack, right? So bending tensile stresses. So for this particular bending tensile stress, concrete will start the cracking. So that will the initial cracking. The entire cross section of the beam resists the bending with the compression on one side and the tension on the other side. So let's consider one of the RCC member like a beam. Depth of the beam is the D, depth of the beam is H, and so these are the depth from this particular reinforcement to the top fibers, right? So let's say here this will be the neutral axis. So you can say here these are the compression fiber, the top fiber, these are the bottom fiber. So that will be the tension. Here we can define the neutral axis. So how do you define the neutral axis? There should not be any tensile forces. There should not be any compressive forces. So in this particular region, there is no tensile force. There is no compressive force. Therefore, we can define which will be the neutral axis. So here you can say compressive strain, and here because of the reinforcement, so the strain is going to happen for the reinforcement. For this, so it was the strain, and this is related to the stresses. So in this particular region, if you do the stress block diagram, so it is this particular compressive stress is going to happen from the two-thirds of that particular distance x, right? And here the tensile force is going to develop for this particular structure. So we can say concrete and steel both participate in the resisting of the forces. So which will the tensile forces. So here the concrete is also getting the giving the contribution, and the steel reinforcement is also giving the contribution in order to resist that particular tensile. So it was the uncracked section, but let's discuss about the cracked concrete section. As the load is increased, after the modulus of rupture of concrete is exceeded, the cracks begin to develop in the bottom of this particular reinforcement. So that is the compression. As the load is further increased, this crack quickly spreaded up to the vicinity of the neutral axis, and then the neutral axis begin to move upward section, right? The cracks occur at that placing along the beam where the actual moment is greater than the cracking moment. So here we can say for this particular reinforced concrete structure, once you are applying the uniformly distributed load, right? So you can see what is the bending moment diagram. So here you can say for this particular central span, so maximum bending moment is going to develop. But once you are going closer to the support, so moment is going to get zero. So here you can say the maximum tensile compressive force, compressive strain, and the maximum compressive strain in the bottom fiber also. So these are from the stresses. So variation of the stress and the strain distribution from this particular service load. So that is the gravity load. So that uniformly distributed loading. So another thing, let's cracks due to the import. Right? So earlier what we were discussing, the cracks due to the only forces, right? So now cracks because of the imposed deformation and some restraining factors. Sometimes if your wrong calculation of the structural design of the level, restraint may result in the wasteful design, or it may be the over design or maybe the under design, which will be leading to the unacceptable cracking also, right? So once you are doing the structural calculation also, if it is your sometimes your assumption is not right or wrong, or sometimes if you are doing the over reinforced section or under reinforced section, and here in the structural design, for example, if you are considering the simply supported structure or the fixed support condition, right? So the bending moment will be different, deformation will be different. Let's consider, for example, a difference in restraint factor point 1 from, say, it will be, let's say, point 0.5 to point 0.6, which will be result in the 20% increase in the estimated restraint strain, right? So if you are considering, let's say if you are considering the restraint factor point 1, now if you are considering point 0.5 to point 0.6 in between, so it will increase the 20% estimate, and which could make the difference between no cracking and the cracking, or acceptable or unacceptable cracking remain. So here you can say age restraint. So this both age are restrained and restrained here, right? So here only one age restraint, and here the both end are restrained. Let's say consider these are the new section and these are the old section. So both have been restrained. the strain will be the different. But here, let's say old concrete is here, and so here both the saying are fixed support, so that crack pattern will be different. Intermediate restraint, for example, let's say these are the simply supported beam and these are the continuous beam, so the restraint will be different, so the crack pattern will be. So concrete crack controlling, so how we can control that particular crack in the beam, so which is because of the increase in the shear stress which appear near to the support, right? So let's consider one of the simple supported beam or the column example. So the concrete stress is developing near to the support, right? So if you see here, the lateral reinforcement spacing, it should be smaller in here, that smaller reinforcement spacing. But here, if you see in this particular region, lateral reinforcement spacing will be higher, because if you see it, like what is the bending moment diagram of this particular structure, right? So here at the near the support, the stress and the moment is going to get zero, but here the maximum bending moment. And if you see here, the that is the shear force diagram, right? So shear force diagram, there is no shear is going to develop, right? For this very less amount of the shear, but the high shear force is developing close to the support, and then maximum bending moment is going to develop at the center of this particular beam. So these crack are also called a shear crack, which are inclined to the 45 degree of the horizontal. So these are the diagonal cracks, so that we can consider the shear crack. The shear crack is the maximum distance of the d by 2 from the support, where the d will be the effective depth of that particular beam. So this particular section, you can say this crack can be avoided by providing the additional shear reinforcement near the support where the shear stress is maximum. So what we have discussed for that particular simple supported beam, and the if you find out the shear force and the bending moment, so here the shear force is maximum near to the support. So these are the diagonal shear crack is going to develop here. So if you can provide the proper lateral reinforcement in the near the support, so you can try to control the cracks, right? So this way we can control the cracks, and see therefore we are providing the bent up reinforcement, right, in order to resist that particular shear stresses. So other thing is that how we can control, let's say rebar helps to keep the crack small, right? So if you are providing the reinforcement, for example, let's you are providing that reinforcement 25, right? And the diameter of the reinforcement is the 25 millimeter, and the spacing is the 300 millimeter. The spacing of that particular reinforcement is 300 millimeter, and now instead of that particular this reinforcement, let's say area of the reinforcement you keep same, but you are providing the 13 number reinforcement, and that spacing should be 150 millimeter, right? So now you are reducing the spacing, so which will help to the controlling the clamp. So here same area of the reinforcement and the same capacity, right? So area of the reinforcement as will be the same in the both the section, but now you have reduced the spacing, you have reinforcement diameter also, but here the larger bar larger spacing, right? But smaller bar smaller spacing, so which the rebar will help to close this space. The rebar will do a better job, which will keeping the cracks small, right? So how the we can reduce the crack, or how we can control the crack, like small rebar reduce crack width about 50% in the concrete structure, right? So this is the main thing. So therefore during a structural design we will have to take care, so we can control. So similarly here also, like how to find out the cracking, right? So crack width, so crack width between that the spacing of the cracking multiply by the strain. So how we can find out the strain? So that is the strain is the ratio of the change in length to the original length. So this way we can reduce the crack spacing, use the smaller reinforcement what we have discussed earlier. We can use the smaller diameter of the reinforcement, and we can reduce the spacing also, right? So reducing the strain, use the partial load factor also, right? So working stress also, like a design of the reinforced concrete structure, the limit state of the serviceability, we are utilizing the partial load factor. So this way we can control this particular cracks in the reinforced concrete structure. So this all the crack we can control how we can providing the reinforcement so during the structure. So like crack control without a direct calculation, without doing any calculation, how we can control the crack according to the Euro code. So crack control due to the flexure, which may be achieved in a two ways: limiting the maximum bar diameter, what we have discussed, right, and limiting the maximum bar spacing. So you can reduce the diameter of the bar, you can reduce the spacing also. So you can how like if you can say here like a maximum crack width is 14.40 millimeters. So here for the diameter of the bar is 40 mm, so maximum spacing will be 300. But now if you are reducing the diameter of the reinforcement, so similarly you can reduce the this particular bar diameter also. So for this particular crack, so we can say the tensile stress is also increasing, right? So we can say for the maximum width 0.30 millimeter, so maximum diameter, so we can keep the spacing should be 300 millimeter. So if you are keeping the diameter of the reinforcement is 80 millimeter, 8 millimeter, right? So how the crack is width is going to get decreasing. So where cracking is due to the restraint, use only the limited maximum diameter of the bar. So here, without doing any calculation, we can control the crack. So that way, how we can provide the reinforcement. So let's say another thing where with the graphical representation. So we can say bar diameter here. This graph related to the bar space. So x-axis that is the reinforcement stresses, and the y-axis that the maximum diameter of the bar. So here you can say if your crack width is 2.2 millimeters, so that the maximum diameter of the bar should be about 6 to 8. So at that time your tensile stress will be about the 320 Newton per millimeter square, right? So here diameter of the bar you can choose the diameter of the bar because you can consider, for example, width of the crack is a 0.2 millimeter. So what would the diameter of the bar? What would the tensile stress is also? Similarly here for the crack that reinforcement spacing also. So here we can say bar spacing if you consider 100 millimeter. So at that time for the 0.2 millimeter crack, so the tensile reinforcement it will be about 230 megapascal. So we can say here stress is due to the quasi-permanent action of the loading. Stress is due to the quasi-permanent action of the loading. So crack calculation we can say how we can calculate the crack. So what we have seen earlier, that is the spacing of the cracking here multiplied by the strain limit. So you can find out the crack width. So according to the Euro code, so you can find out the crack width. So here SR maximum spacing of the crack. So this way you can calculate the crack spacing. So here the C is the nominal cover of the reinforced concrete structure. K1 and K2 are the factors so which is related to the high bond bars, right, and the tension as well as the bending also. So here like rho effective also, that is the reinforcement area of the steel divided by the area of the concrete section. So you can say flexural restraint. So this way you can calculate the crack width as well as without doing any calculation the length. So crack width or the flexure also you can apply the using this equation also you can able to calculate this particular crack. So if your factor zero point 0.6 for the short term loading, if you are considering long term loading, so yeah, the KT factor will be zero point 0.4. So similarly you can calculate all the crack width. So here the all the value is given here like typical value of the alpha E are 6 at the 3 days and 7 for the 28 days and the 12 for the long term loading. So for this particular equation, once you substitute the value, so you can calculate the strain. So how much the strain is going to develop for that particular reinforced concrete structure under the action of that particular gravity loading. So we can say when cracking occur, no creep has taken place. So we can say alpha value of the alpha is recommended about the 7. And here we can consider that the modulus of elasticity of the reinforced concrete structure for the steel, mild steel material should be 2 multiplied by 10 raised to power 4, which is equal to the 200. So this way we can calculate the strain like a strain in the concrete, right? So the plane section remain plane. That was our assumption, like proper bonding also. Using this specific equation according to Eurocode, we can calculate what is the width of that particular. So that is now related the code, Egyptian code. So how we can calculate the crack width? So using this specific equation, we can calculate the width of that particular crack. So WK, that is the coefficient, and SRM, so that is the average stabilized crack spacing, as epsilon SM, that is the steel strain of the reinforcement, beta, that is the coefficient, so that it will be 1.7 for the crack induced by the loading, and the beta value we can consider 1.3 for the crack induced by the restraining. So whichever is smaller, so less than 300 right? So that the value of the beta we can calculate. So the mean strain in the that particular reinforced concrete structure we can calculate using this specific equation. So what is the Fs? So that is the tensile stresses. What is the Es? So that is the modulus of elasticity. So all these things, like we can calculate the value beta 1, beta 2, and eventually we can find out what is the strain capacity of this particular concrete structure. So this way we can find out so strain using the this particular Egyptian code. So now crack control using the SCI, right? So SCI is given this specific equation to find out the crack width, right? So for this particular equation, beta is equal to ratio of H minus X to the D minus X. Beta is here 1.2. So beam may be used to compare the crack width obtained in the flexure as well as the axial tension. So area of the reinforcement A0, AE, that is the effective area in the tension, right? And now we can calculate the value all these things using this particular equation, like crack spacing. So AS will be the, like, propose the following equation by the ACI 381, and then which was version of the 2005, 2018. Now 2019 is little bit different, right? So AS, which is equal to spacing of the reinforcement, we can, or the spacing of the crack we can calculate. So maximum spacing of the reinforcement closer to the tension side of this particular reinforced concrete structure, and C, that is the least distance from the surface of the reinforcement to the spacing of the reinforcement. Let's say how we can calculate the crack width using the British standard also. Like the design surface crack width, we can calculate using this specific equation, right? So once you have to calculate this particular crack width, so according to the BS, so you can first you can find out the strain capacity, right? Right, this, so we can calculate that is the how much the strain we are getting and what will the crack width according to the British standard, right? So our Indian standard is also related to the combination of the American standard to the British standard. So how we can calculate according to the IS 456? So the IS 456 is given, that is the one of the annexer F, so which is given some equation how we can calculate the crack width. So using this particular equation, we can calculate the crack width. So here ACR, that is the distance from the point considered to the surface of the near to the longitudinal bar. C minimum, that is the minimum cover to the longitudinal reinforcement. Epsilon M, that is average C minimum here. Minimum cover to the tension here, right? And H is the overall depth of the member, the depth of the neutral axis. So you can calculate the ACR and the sigma m. So using this particular equation, we can calculate all the value. So here this value, diameter of the reinforcement, the cover, and the S spacing are obtained from the section of that particular member. So that value we can calculate from the sectional analysis. So for the crack width, like strain capacity for the rectangular tension zone, we can calculate what is the average strain for this particular equation, right? So average strain you can calculate by applying this equation. So now the strain you know, the stresses you know. So now we can able to calculate what is the crack width according to the IS 456. So cracking of the concrete should not adversely affect the appearance of the durability of the concrete structure, right? So there should be permissible limit. So here we can say surface width of the crack which should not be greater than the 0.3 millimeter for the normal condition, right? Normal condition, which means the structure has been protected and not exposed to the aggressive environmental condition. So at that time, the crack width should be 0.3. So sometimes the moderate and the mild environment, so the crack width should be less than or equal to 0.2 millimeter, right? So this is according to IS. In the sum of the case, if the environmental exposure condition is very severe condition, so at that time the width crack, so that should be less than or equal to zero point 0.1 millimeter. So now that was related to the crack control for the structural design, right? So how we can control it. But let's say for the construction practicing also, how we can control the crack in the construction practice also. Here you can see these are the welded rebar, right? So roll out the reinforcement also, and here the deform bar. So if you are utilizing this kind of the reinforcement, so you can close this particular control the crack, like provide the closely placed reinforcement. So this particular reinforcement is the closely placed, but here is the these are the welded reinforcement also. So now you can roll out this particular reinforcement. So here you can say spacing of the reinforcement it's very close. So now this way we can control the cracks very small, improve the durability of that particular concrete, or you can increase the depth of that particular section also, so increase the cover concrete also. So you can use the better quality of the concrete also, for example, let's say high strength concrete also. So this way we can make durable concrete structure also, right? So concluding the crack, so crack width, so what we have discussed, it should be less than the 0.2 millimeter for the moderate to the more mild exposure condition, zero point 0.1 for the severe exposure condition, and how we can limit the tensile stresses in the steel reinforcement, right? So like what we have discussed earlier, minimize the spacing, right? Closely spaced reinforcement, and we can utilize that the diameter of the reinforcement also should be smaller. Like here you can say these are the reinforcement pattern, right? So lateral reinforcement, the spacing of the reinforcement should be smaller, right? So that way you can control the crack. And you can provide the proper joints also, right? Once you are providing the proper joint also, so you can control the cracking also. Here you can say so cut joint here. So these are the some of the cracks is going to develop, right? So minimum the depth of the is so cut joint, so we can provide the joint, it should be 1/4 of the depth of the reinforcement. So whatever the depth of the reinforcement d multiply by the 1/4 or say 0.25, so we'll have to create some of the so cut joint also. So this way we can control. So another crack also, concrete beam due to the tension, right? So because of that corrosion, so there is a reinforcement is going here the parallel to this in this direction, like longitudinal reinforcement to the develop because of the corrosion of. So how we can stop the corrosion? So due to the reinforcement, corrosion can cause falling of the concrete, which is in the severe cases also. So which can be prevented by the applying the good quality of the concrete as well as the proper reinforcement detailing as well as the proper curing condition also. Like here, adequate reinforcement design, proper reinforcement cover, good quality of the concrete as well as the proper that curing condition. So this way we can control the crack in the construction practices also. So cracking due to the bending stress in the beam. So because of the bending stress is the crack is happening in the flexure crack. So these are the cracks, the flexure crack. So here the shear crack and these are the flexure crack because of the spanning. So now you can reduce the span of the structure also, or you can provide the close displaced reinforcement at the support condition. And here the spacing of the reinforcement will be higher, right? Because there is a less shear force is going to do now, and the care should be taken during the beam design. So the probable load combination, like here, according to the code of practice, we have to consider the probable load combination also. So this way we can control the particular depth that crack will. Like under reinforced section of the beam is the main cause of the cracking, right? So if you are designing your structure under reinforced section, that is the main cause of problem of the cracks, right? So cracking due to the compression failure of the beam, which appear at top of the beam if the beam is over reinforced, right? If the beam is over reinforced, the top of the beam, so this the crack is happening because of the compression failure. So in this particular stress block diagram, we can understand here, like here, so the crack, the structure should not be under reinforced section or should not be over reinforced section. So this way we can control the crack during the structural design as well the construction practicing. In which capacity of the beam compression is capable of the load carrying or the additional compressive stress. So in the construction practice, how we can control by providing the proper quality of the concrete, like inhibition of the water evaporation here, like water evaporates like a shrinkage expansive material. We can use the proper quality of the water, proper durability, like proper curing condition, and the proper supplementary cementitious material also, environmental exposure, structural regulation also. This way we can stop that or we can control the cracking, like cracking resistance, like evolution of the metal, like a driving force is force to resistance, like a capillary negative pressure, temperature shrinkage, like temperature shrinkage, which is related to the heat of the hydration. Because if you are doing the mass concreting, right, so there is a lot of exothermic process, like heat will be generated. So if you are utilizing the normal process, which will not able to get the neutralized. So in that particular cases, we should have to use the ice during the concrete. So this way we can neutralize the heat of hydration. Early age curing also, like you have to provide the early age curing. So here the plastic stage and the hardening stage also, like monomer layer with a high evaporation capacity and the hydration degree also, like high performance curing material with a hydrophobic pressure. Early as cooking, so you can say air and the water here, water will get evaporation, so you can save the monomer layer. So you can see here water evaporation, but the time, so you can see here that initiation of that particular character 75%, that initial time, so inhibition of the evaporation by the 75% of that cracking. Early as curing, like in this particular area, no curing, so the cracks is going to develop, right? So here this kind of the crack is going to develop, like if, but if you are applying the proper curing, right? So this is the curing material here. So non-curing here, these are the curing material. So here we can say the pore negative pressure will be increasing, so which way you can delaying the cracking also. If you are utilizing the 30 megapascal cracking, so 4-day curing 20 hours, so initial crack will be 10 millimeters. If you are applying the 7-day curing, so the crack width will be 0.01. Right? So this way we can control the cracking. Let's say consider reference material, one expansive agent. If you are utilizing some expansive agent during the concreting, if you are utilizing some expansive agent, so here that way we can control the crack with this particular expansive material. Crack control using the heat of hydration, right? So we can utilize water reducing admixture, so that way we can reduce the cracking also, like multi hydroxy or the polyhydroxy containing. So this way we can say calcium hydroxide. So this way we can control the crack. So like absorbing the calcium calcium hydroxide in the additive agent. Right? So that way we can say inhibition of the calcium hydroxide crystallization, and then you can reduce and the C3S phases. So this is the that both compound. So during the production of the cement, we have to reduce this way. So that way we can reduce that particular heat of hydration. Main thing you can control the cracking. So cracking control with the providing the proper admixture also, right? So if you are providing the proper admixture also, which will be reducing the heat of hydration, and eventually we can control the cracking. So here for this particular diagram, hydration the heat, and the x-axis that is the time period. So like if you are utilizing the proper material, so that way controlling the process of the cement hydration, controlling the process of the cement hydration, which will improve the capability of the temperature control or the mass concrete eventually, which will increase the durability of that particular part. So till now, what we have discussed, right? So we have been discussed about that how to control the crack, even the structural design, even in the construction practices. So structural design, what we have discussed, like a basic of the crack formation in the concrete structure. We have discussed what is the crack mechanism, right? How the crack is going to develop, and the different type of the cracks. So different types of the cracks that were the before the hardening as well the after hardening. So that we have discussed the crack mechanism and the different type of the cracks. After that, what we have discussed, we have been discussed the causes of the crack formation. So how the crack is going to develop and how we can control the crack using that limit state of the serviceability and the design assumption also. We have discussed the limit state of serviceability, that is the what is the crack width, what is the permissible deformation. So that we have discussed in the crack formation. So how we can control the crack of this particular reinforced concrete structure. So we have discussed with the different code of practice. So we have discussed the ACI standard, British standard, Indian standard, Egyptian standard also, right? So that way, how we can find out the width of the particular crack in the reinforced concrete structure. After that, we have discussed crack control during the structural design in the RCC element and how to control or the measure the crack formation in the reinforced concrete structure. Then finally, we have discussed the crack control and measure during the construction practices also. The construction practices, which means you have to provide the proper joint also, right? Proper curing also, proper construction material also. You can use the high strength concrete. You can utilize the corrosion inhibitor also. You can utilize that water reducing admixture also, like a plastic super plasticizer also. So which means you are controlling the cracking by construction practice also. Now you can provide the proper supplementary cementitious material also. So the if you are utilizing the fly ash, so that is also reducing the shrinkage crack in the early stage of the hardening also, right? So this way we have discussed measure of the how we can control the formation of the crack and how we can control that crack in the structural design as well as the that section also. Now, so now we are just done with the lecture. So please let us know if you have any question regarding this webinar. Right? So then the floor is open for the question answer. So thank you very much everyone for patiently listening. Right. So you can contact me by email also, by telephone also, right? Most of the time is I'm available in the office, but like even online I'm also available. So whatever the difficulty question, please feel free to ask me or we can discuss in the road. Thank you. Thank you very much. And then now we'd like to acknowledge that Gandhi College of Engineering, Professor Mayank Patel and the Professor Darshan Mehta for providing the opportunity to share my knowledge to the technical people like consulting engineer also, student also, faculty also throughout the country, and some people maybe have attended from the abroad also. So thank you very much.
Thank you, sir, for your kind session, informative session. Now we have 4 to 5 questions in the chat box that we will discuss. Uh, Differential evaluation can be carried out for cracks exhibiting the almost same characteristics. That is, a crack is there which confuses with shear crack or another type of crack. In this case, how to evaluate differential?
Okay, yeah. Some of the cracks. Let's start from how differential evolution crack can be carried out for the crack exhibit. How differential evolution can be carried out. Cracks exhibiting the almost same characteristic. Crack is there which confuse its shear crack or another type of crack. In this case, how to evaluate the differential crack? How to evaluate the differential crack carried out for the crack exhibiting almost the same characteristic. So differential crack, so like that is related to the settlement, right? So because of the settlement all the crack is happening. So at that time, how we can evaluate the cracks? So we need to measure the cracks, right? So evaluation of the cracks, which means we have to measure the cracks. So you can apply some of the strain gauges also. You can use the LVDT also. Then you can measure the crack width. Even if you can measure the crack depth also, right? So that way differential crack. So because of the settlement, so that is related to limit state of the serviceability criteria. And so once we can see here, so during that construction practice also, how we can measure the crack. So main thing you have to measure the crack. You can apply, that is the strain gauges. You can apply the fiber optics sensor also, and you can use that LVDT also. We can control the cracking there, and you can measure the crack. So another crack question: how to control the settlement crack in the concrete pavement? Yeah, so that's great question. How we can control the settlement crack? So at that time, your sub-base materials, right? So sub-base material, if it is getting settled,